All right, so today we're going to talk about ceramic structures, focusing on ionic ceramics. And this first module, I want to talk about the factors that contribute to those structures. So let's start out with a quiz question. So, what factors do you think are critical for determining the structure of ceramic compounds? So, this is where I want to see what you know about this before we discuss the various factors for ionic ceramics. So, go ahead and mention those, write those in the quiz, and then come back and we will talk about the factors. All right, so let's look at the factors that go into this. And so just because you wrote something different doesn't necessarily mean it's wrong. Some of these are just another way to phrase these rules. And then also these aren't the only factors that go into determining structure. So just because you wrote something different doesn't necessarily mean it's wrong. But the first things that we're going to look at are the crystal stoichiometry. So that is how many cations, how many how many cations and anions based on charge. So this is all kind of related to charge neutrality. So all crystals must have be electrically neutral. So that's the first important part that has to happen. Also, we're going to look at the radius ratio, and that's defined as the radius of the cation over the radius of the anion. So this might be something you remember from MSE 201. And so this is basically size consideration, the relative size of the cation and anion. And so this, the idea with the size consideration here is that it maximizes attractions between Coulombic forces between dissimilar charges, and it minimizes the repulsion. And so, even though we're talking about size, it also has to do with the bond force and energy, obviously. And then the last thing is what we just kind of term propensity for covalency. And so we're going to find that covalency kind of manifests itself as tetrahedral arrangements. And this basically can occur even if it doesn't have the necessary or proper radius ratio. So covalency kind of messes up, so to speak, these other two rules. All right, so let's sort of start in the middle here. Let's start with number 2, and let's look at the size ratio. And so I've got a couple different scenarios here. And so, again, think about the relative size. So the cation's the smallest here. The anions, which are the larger of the two species, is the one surrounding it. So basically, in all these scenarios, the cation is increasing relative to the anion. So that ratio is getting larger. So with the smallest cation ratio, you see that the central cation in the middle, it's not touching the 4 anions around it in this planar configuration, whereas the anions are touching. And so if we think about the different bond forces, right, the anion bond would be repulsive and they're touching, whereas the positive to negative bond here, they're not touching, so they're not as close as possible. And so this is going to lead to anion repulsion. And so this isn't a stable configuration. So this is not stable. Here, this is the case where the cation has grown in size or increased. We now have a cation at the right size where it's just touching, right? So this is kind of the lowest stability or the critical value, right? Because before the cation wasn't touching. So here we have both, right? We've kind of maximized, we have now touching of the cation and anion. So that bond has increased, but we still do have the anion repulsion. So this is stable, but also this is stable here as well, where the cation is touching the anions, but it's kind of forced the separation between the anions. So that would minimize the anion interaction in this case. All right, so let's speak a little bit more to the sizes. So we know that as we'll sort of see with the visual in the next slide, cations are typically smaller than anions. So that's our general rule of thumb. The radius of a cation is smaller than its corresponding atom as well, right? Because electrons have been removed and they basically consolidate closer to the nucleus. We have the radius of the anion is larger because we've added electrons, and that becomes more repulsion in the cloud. So we've added electrons there. And then the radius increases with increasing atomic number, the Z number that we sometimes refer to. But if you look in the middle of the periodic table with those transition metals, those often behave differently. And so we'll see, if you look at the periodic table, you might see some differences there. Okay, so here's the chart that kind of shows you what we're talking about. So the red being the positive, so cations, and then the gray in both cases being the neutral species, and then the blue being the anions. So you can see here that in general, these blue anions are much larger than the red cations. But if you go down, right, increase the atomic number, you could get to a case where one of these is as large or larger than some of the anions. So again, it's a general rule, but there are cases where the cation can be larger. So something like rubidium down here.